Hi, everyone. Welcome to the weekly colloquium series of the C3.ai Digital Transformation Institute. So our institute is dedicated to the promotion of research on the digital transformation of society through the use of machine learning, artificial intelligence, IoT, and cloud computing. The institute is a partnership of a number of institutions. The two industrial partners are C3.ai and Microsoft. I should say the two leading industrial partners. And the universities involved are Illinois, Berkeley, Carnegie Mellon, MIT, Princeton, the University of Chicago, the National Center for Supercomputing Applications at Illinois, Lawrence Berkeley National Lab, and Stanford University. We started this colloquium series a few weeks ago. We've had a number of great talks, and we have a number of wonderful talks still forthcoming. The next week's talk will be by Zoe Rapti, a mathematician at University of Illinois, followed by Vince Poor, Saurabh Amin, Sanmi Koejo, Raid Ghani, Sendil Mullainathan, and Ziad Obermeyer, Herbrand Cedar, Jennifer Listgarden, Emmanuel Candace, Ziv Bar Joseph, Renee Vidal, Nancy Amato and her collaborators, Stefana Paraska and Karina Ternita, and Karen Chappell and her collaborators. So as you may have noticed, many of the talks are COVID-19 related, but there are also a couple of other talks, for example, as in the previous slide by Emmanuel Candace, and would be more general. So we have a great seminar colloquium series, and I hope you can continue to attend them. I also would like to announce an exciting new workshop series that we have started. The first one of these will be held between September 8th and 11th from 1 p.m. to 5 p.m. Eastern Time. This workshop will explore the similarities and differences in the mathematics of the dynamics of epidemics, opinions, and misinformation, which popularly people call fake news. So the workshop is titled Epidemics, Opinions, and Misinformation, the Analytic Foundations of Dynamics over Networks. It's organized by Devabra Cha at MIT and Lei Ying at University of Michigan. And we have an all-star cast of speakers: Noah Friedkin from University of California, Santa Barbara, Matt Jackson from Stanford, John Kleinberg from Cornell, Naomi Leonard from Princeton, Laurent Moussoulier from Microsoft Research and INRIA, Elhanan Mossel from MIT, Vince Poor from Princeton, Weina Wong from Carnegie Mellon University, and Tauhid Zaman at Yale. So please look at the schedule, and you may have to register, but other than that, attendance is free for this workshop. Just before I introduce the distinguished speakers today, I just want to tell you briefly about the format of this colloquium today. There will be a roughly 40-minute presentation, followed by a 15-minute question and answer session. At least that's the way I have written it here. But the speakers today told me that they welcome questions during their talk. For example, there are two speakers, and there will be a transition time from one of them to the other. That would be a natural time to ask some questions before the end of the whole presentation. Please use the Q&A feature to ask questions, and you can upvote any question that you like, and we'll try to answer as many questions as time will permit. So without further ado, let me introduce the talk. The title of the talk today is Targeted Dynamic Interventions in Networked Epidemic Models. And we have two great speakers. The first one is my good friend, Asu Ozdaglar. She's the head of EECS. She's the MathWorks Professor of Electrical Engineering and Computer Science. And she's the Deputy Dean of Academics in the Schwarzman College of Computing. She's an expert on many things, including optimization, game theory, distributed control, distributed optimization, and network analysis. She has won many awards for her work, including the 2008 Donald Ekman Award of the American Automatic Control Council. And if you look at the list of people who have won the Ekman Award, they're all the who's who of researchers in the control area. The other speaker today is a young superstar, Francesca Parisi. She recently joined the School of Electrical and Computer Engineering at Cornell University as an assistant professor. Before then, she was a postdoc with Asu at MIT, and she got her PhD from ETH. She has also won many awards for her work. In particular, she won the ETH medal for her doctoral work. So now I'd like to turn it over to Asu, and then and I guess Asu will transition to Francesca. So I'll stop sharing, and then Asu, you can start the sharing.
Hello. Okay, start my video. Okay, I guess I'm on now. Hello, everyone. Thank you very much, Shrikant and Shankar, for the invitation and for the very kind introduction. It's a pleasure to be here. So let me share my screen and let me do full screen. Okay, excellent. I hope everyone can see the slides. I'm assuming everyone can see it. So,
yes.
Okay, excellent. Thank you. Thank you for the indicator. So I'm very delighted to give this talk with Francesca, who is my, very close collaborator. We work on many different projects together. And this is sort of our work, our project as part of C3 AI that we're very excited about on COVID-19 interventions, dynamic interventions for COVID-19. There was some point where we actually couldn't focus on anything but work on this topic. Now it's a little bit better, but we're going to talk about a couple of the initial work in this area. And this is sort of parts of this work is in collaboration with Daron Acemoglu, Dan Huttenlocker and Emily Mikes from MIT, as well as Giacomo Como and Leonardo Cianfanelli from Politecnico di Torino. So quickly, I'll give them motivation. Epidemic models are playing a central role in understanding the spread of COVID-19, and in particular, analyzing the effects of interventions on limiting the spread of this epidemic. And because we don't have a vaccine or therapeutic cure for COVID-19, our focus has been, our community's focus has been on non-pharmacological interventions such as testing, contact tracing, isolation, and lockdown policies. And if you think about these interventions, these not only have epidemic or public health implications, but also social and economic effects. So our project is really about thinking about these different objectives together, and existing approaches have not yet fully integrated this epidemiological dynamics with social and economic costs, and except for a few very recent papers, try to understand optimal dynamic policies. So this project is about optimal testing and lockdown policies and trading of economic and public health costs in the context of network SIR models. And in this talk, I will basically give an overview. We will give, Francesca and I will give an overview of three initial works in this space. The first one will be modeling the structure of interactions in a community by creating pods or living groups, which is especially relevant for university campuses. We're going to talk about testing within a pod structure, and then also present some initial results on optimal dynamic lockdown policies. So before we dive into the details, let me quickly give a brief overview on epidemic models, just to give some background and fix our notation. So epidemic models broadly, it considers a population of N agents, and a common feature of these models is the existence of these compartments, most common being susceptible, infected, recovered, although this could go on, quarantined, exposed, and so on. And these compartments, susceptible, for instance, captures individuals that are healthy but can become infected, infected are clearly infected, and can become recovered, and so on. So state of an agent can be one of these, S, I, or R. And stochastic models consider evolution of agents as their states move from one compartment to another randomly with some infection or recovery rates. So if you look at this simple SIR model, an agent can randomly move from S to I with some infection rate beta, that's the result of interactions with infected agents, or can move from I to R with some recovery rate, which is basically a result of recovering from the infection. So this is a Markov process, a very large one. If you think about three states with N agents, it's 3 to the N, it's not tractable. So what we do in general is we assume instead large population of homogeneous agents and track the fraction or mean of individuals in different states. So that sort of brings us to this deterministic population level or mean field models. And that will be our focus also in this work. And here is the classic SIR model. Much of our work will depend on this, will be based on this. So let me quickly go over this. So this has three compartments, and the equations defining the dynamics or the evolution of states are given by this. So the number of susceptible individuals or agents change by this equation minus f of I times S, which represents the new infections. And f of I is this force of infection, rate at which a susceptible agent gets infected. And we can express this term as some transmission probability. This is the probability that a susceptible agent gets infected when they meet an infected agent, times number of daily contacts, times the probability that that contact is with an infected agent. So that's exactly how, the rate at which the susceptible agent gets infected. And infected agents grow by that amount minus the recovered agents, and recovered agents grow by the recovered agents. And many people are talking about this R0, which is the number of secondary infections. Essentially, this is the average number of infections caused by an infected agent if we just drop this agent in a population consisting of susceptibles only. And that's given by this lambda times H, which is the beta term, rate of infections caused by an infected agent, times, so this is the number of infections per day, times the number of days that the agent is ill, 1 over gamma, which is the 14 days in this case. So this is the beta over gamma, and if this is less than 1, we expect this infection to, asymptotically die down. So we can enrich the model by adding testing to it, and theta is the testing rate per day, number of tests per day per agent. And the only difference from the previous model is we also detect some of the infected agents with theta times I, which we move to some quarantined state minus the recovery, and we also pull recovered agents from the quarantined agents. And in this case, time an infected agent is circulating becomes 1 over the time an infected agent circulating becomes gamma plus theta, so the R0 is updated to be beta over gamma plus theta in this case. So that's sort of the quick background, and the talk will have 2 parts. I'll talk about the first part and Francesca will focus on the second. The first one will be about social distancing through living groups. And this is actually a question that was posed to us by MIT, by our chancellor. Can we actually think about creating living groups? How do we analyze the spread and look at the testing requirements? And the second one will be the lockdown policies and basically thinking about trade-offs between economic and public health outcomes. And Francesca will talk about a number of different policies and talk also about how we analyze their performance, both in terms of economic and epidemic costs. And these are dynamic policies. That's a function of the underlying state of the system. So let me quickly start with the first part. As I mentioned, this was very, motivated by MIT's plans for fall reopening. And much of our classroom instruction is online this fall. But sort of the question that kept us quite busy is an important aspect of the on-campus education in addition to classroom instruction is our students working with peers in groups, doing problem sets, projects, and other activities. So basically the idea or the question that was posed was, can we reduce student isolation by creating these residential pods or living groups or cohorts in residence halls such that these are families? They don't require social distancing within the group, but they require social distancing when interacting with people outside the group. So this was the question, and our goal was to understand how we can model the spread of infection across these pods. Well, these students will still have some in-person elements or classes, which is the academic interactions. And secondly, these students are young people, so they will basically have some form of non-compliance in interacting with individuals outside their pod. So the question is, can we see the advantages, can we characterize the advantages and disadvantages of these pods? What are the required testing rates? Can we study pods of different types, organized in different interaction structures, different sizes, behavior, and compliance? So the first question then one needs to think about in this context is, how do we model the pod structure? So it's a networked model depending on the interactions, but there are 2 ways we can actually think about modeling pods and tracking infected individuals. One is at the agent level. So we can actually say I1 is the number of infected students in pod 1. And that's sort of what I refer to as the agent-based model. But we can also think about types of pods. And we can think about, for instance, type 1 could be first-year students in dorm Baker house. And we can think about, number of pods within a type. And that's the pod-based model. So why am I doing this? Because in the agent-based, we always thought about doing these pods with very small number of students, 2, 3. And if we actually do that, mean field approximation or mean field models we're going to use with an agent-based model will be very poor. I mean, this is because, as I mentioned, mean field models are used for a large number of agents. In this scenario, they're not applicable, and we actually verified this through stochastic simulations also. But probably more importantly for our purposes, if you model things at the individual level, that will actually lead to a model where you're thinking about testing per individual. And that's not optimal. What we want to do is basically test, if you're thinking about creating pods, and within the pod, there's going to be a very fast dynamic. So we can actually, it's a good approximation to model all the agents in one pod to be in the same state. So you don't want to test everyone, but just one person per pod. So that pod-based model, I think, also brings us to more, smarter testing where we actually do the testing at the level of the pods. So for these two reasons, we actually we did our analysis following a pod-based model. And, we can have in this model multiple types of pods. Pods can be of K types, maybe first-year students in Baker House, second-year students in Baker House, or fraternities. And we can define this as fine as we want, with the caveat that we have to be careful so that there are enough pods per type, so that our analysis can capture the stochastic model, in a good way, in a reasonably well-modeled way. And we assume now the pods of type K have NK students, so in this example here in blue, it's basically 3 students within this pod. And we assume now that because we're capturing everything at the pod level, students within pods behave similarly. So these are homogeneous agents within the pod. And the types of interactions we considered were social interactions, which is across the pods, essentially modeling non-compliance. And this is sort of, we modeled it with a transmission rate of 0.1 to 0.3. And there's also academic interactions. This is, short and controlled with masks, and MIT has very strict distance requirements. So this is basically going to be a less, we modeled this to be a smaller transmission rate than the social interactions.
Awesome.
Yes.
Since you said we could ask questions in the middle, I have a quick question. So, yes. So in the concept of a pod, so they act sort of like a family. So people within a pod don't wear masks and they interact with each other and so on.
Exactly.
And so then this could also be then useful to model not just MIT's student pod, it could also be at the level of families and households, right? So,
exactly. Okay. And there is some work also looking into that. I'm explaining it in the MIT, terminology, because I'm assuming this is of interest to a number of people from universities, but this is definitely for, living groups, essentially. And the main assumption we're making here is that everyone in the same pod is in the same state. If one person is infected, all is infected. So what this is missing in the model I'm presenting is the within pod dynamics. But that's, epidemiologists, we talked to some, and that's so fast that it's actually a good approximation to think about everyone being in the same state. We have some work which is also thinking about extensions, but so far we're assuming that everybody in the pod is in the same state.
Thank you.
Perfect. So, and then I'll go over these interactions a little bit quickly. So we basically modeled, this is the academic interactions. A student in a pod of type K interacts, let's say, has 5 interactions with type K prime. This is something that we can actually pull from registrar's office, which, labs and classes they take together. And NK is 4 here, 4 students or 4 agents, let me use in this group. So the number of daily academic interactions of a pod of type K is HKK, which is NK times HKK. And similarly, I'm just gonna go over this. The little h is the number of social interactions a student has with students in pods of type K prime. And the capital H is the pod version of it, where we multiply it by the number of agents in the pod. We can also assume interactions with Boston, which is another important, sort of cause of bringing infections to the campus. And we can say HKB is the number of daily social interactions with people in Boston, and NK is again at the pod level. So now that we've sort of defined our primitives, we can actually write down our epidemic model for these pods. Now I'm doing everything at the pod level. NK will be the total number of pods of type K. These notation is just number of pods of type K, not individuals, that are susceptible, infected, undetected, quarantined, and recovered. IB is the number of people in Boston, MB is Boston's population, theta K number of tests per pod for type K. And C here is our compliance level. So 1 is perfect compliance across pods. And that means no interactions across pods. And this is just networked a little bit more algebraically involved version of the simple model that I presented before. This is exactly has this SK times the force of infection. Force of infection is now the third term is the easiest. This is basically, remember, transmission rate times the number of interactions times the probability that one interaction is with an infected agent. For the academic ones, you basically sum it over all other pods of type K prime, and for social ones, again, you sum it over all K prime. And you have the testing, recovery, as well as quarantined and the recovered compartments. So how do we analyze this quickly? Basically, this is my slide with a little bit of math. It looks sort of too much notation, but actually it's simple. This is just putting everything in matrix vector form. And then to analyze the stability of this system, we linearize around a particular equilibrium here. And basically, we're interested in the asymptotic stability of this particular system. And that is essentially means look at the maximum eigenvalue of this T plus sigma, which is hard to characterize. And there's this beautiful paper by Diekman from 2010, which says, actually, instead of that, you can just look at T times sigma inverse and look at the spectral radius of that. And actually, this is very cool because this is, you can view this as the, this is exactly the beta over gamma. Rate of infections divided by the, or times the length of illness. So this is sort of the matrix version of that. And if you can just easily characterize this one, it becomes basically the spectral radius of this matrix over here. So now that we have this R0 tilde, we can just write, interesting optimization formulations to reduce R0 as much as possible, given our budget on testing or other parameters. So what insights can we obtain from this model? And I put here a couple of caveats. Francesca is very careful. We need to make sure we're saying that this is a mean field analysis. We have to validate this with stochastic simulations. But we did. And actually, our model is very closely capturing the stochastic model also, which is good news. So the first thing that comes to mind is, do we want to do pods? What are the advantages and disadvantages? And this is a simple example showing why pods are different from not having pods. So scenario 1 is no pods. Students are not in pods. They have HS daily interactions. So if you look at R0 less than 1, that basically gives you a minimum testing requirement to preserve this R0. And the second one is let's organize them in pods, and then they're free to interact within the pod, and they have some 1 minus THS interactions outside the pod because of non-compliance. And that basically gives you another testing requirement. And you can see here by comparing these two blue and red requirements on testing that actually, because now you have reduced interactions when you're in a pod, that helps in reducing uncontrolled interactions. But at the same time, you see that comparing the testing, the recovery piece, that in a pod, because you have more interactions within the pod, effectively the pod recovers at slower rate. So this actually is an effect against pod. So whether or not pod is better depends on, depends on the parameters and which of these two effects dominate. And to actually see that, we can also, quickly plot the testing requirements. Red one is without the pod, and blue one is testing requirements with the pod as a function of the pod size and as a function of the compliance. And you can see that if the compliance is good, then the testing requirements of the pod is much better than not having the pod. But, if the compliance is worse, then, pod could actually lead to a worse testing requirements. And this is because, essentially within the pod, you have so much interactions. You don't have any social distancing that, those interactions overwhelm your system. So, we also put here some unmodeled dependencies in our model. We assume the compliance to be a fixed number. Of course, it depends on N. The larger your pod is, the less incentive you have to interact with people outside your pod. And as I mentioned, thinking about exposed agents, within the pod, there's also some dynamics. Some agent gets the infection, maybe does not infect others for a couple of days. You may catch the person and then, make sure the rest of the pod actually remains not infected. So there's some benefit from that we're not capturing here, which is ongoing work. So we did a couple of other things. This is some cute results I wanted to share. For instance, for one pod, we looked at the testing requirements as a function of compliance. This is to maintain some R0, which is 0.8. So let's look at the 7 pod size of 7. So if the compliance is great, you need to actually, these two are showing the same, same setup. They're showing different things. This is the percentage of pods, and this is the number of days in between tests that you need for each pod. So I like this table better. Let's look at the size 7 pod, and it says basically if you have good compliance, you need to test the pod every 62 days. And as your compliance goes worse, then you go and to this level, which is test the pod every day. And while you have 7 students in the pod, basically this gives you at sort of half compliance, you need to test 1 student per pod every week. So this is sort of what I was talking about, comparing our sort of mean field model with stochastic simulations. This is very, initial for one pod, but this essentially gave us hope that the pod mean field model and the stochastic simulations actually seem to not deviate by much. Of course, there's some variance, but at least, we're capturing the mean properly. And you can also now go beyond this. I just showed you one pod. We can say 2 pods, maybe dorms and FSILGs. And then we model the interactions between, different pods in a dorm. Maybe that's higher. And then with FSILGs, it's lower. You can compute the R0 tilde and you do things like, okay, can we actually decide how to optimally allocate testing between the dorms and FSILGs if I want to keep my R0 less than 0.8? So that sort of concludes the first part. Some remarks, again, this is a mean field model. One should look at stochastic simulations. Results are sensitive to choices of these transmission probabilities. This is sort of very common feature of all the models in this literature. Obtaining accurate estimates, making sure we have, robustness checks around these estimates are very important. So currently under investigation is thinking about optimal testing rate when we have multiple types of pods and, modeling in pod dynamics, as I mentioned, but more interestingly, this is a project which we're excited about. We're also thinking about combining different types of testing. So serology as a surveillance method and combined with PCR testing, which is much more of a diagnosis method. So this is basically motivated by the fact that the testing rate that's given by our analysis was still very high, but can we actually think about this testing to be dependent on the state of the system and then use serology to tell us when the number of infected agents increases so much that we actually maybe use PCR testing more frequently at that point. So with that, let me stop sharing and hand it over to Francesca, unless there are any questions for me.
So there are 2 questions. I'll read them out, but you can also see them on the Q&A box also. Okay. So the first question is by Juan Pablo Gutierrez. Says that he's not totally convinced about the assumption that all the people in the same pod are at the same stage, and there's evidence that not all individuals in the same household, for example, are infected, but only a few. Yeah. How relevant is this assumption for the model? Is it possible to incorporate intra-pod dynamics?
So that's an excellent question, and I completely agree. And I mentioned this before, it's totally possible for one person to be infected and not infect the others. So ours is a conservative version of that, in that assumes everybody is infected instantaneously. The reason we did that is it's much more tractable, because the dynamics of the across pods and within pods are different. So tracking those 2 different dynamics is not straightforward, but we are actually working on it to be able to, and that's what that kind of model will actually give us more benefits that we can obtain from this pod structure. So that's a very good question.
But as you said, it is conservative, right? So if your model says that the testing requirement should be this, that should be sufficient if fewer people are infected.
Yes, but I mean, the issue, Shrikant, is, for some compliance levels as well as some lambda S parameters, the testing actually becomes quite high. So that's why we started looking at these 2, refinements, both in terms of exposed agents benefits coming from the pod, as well as, this other, combining different types of testing to be able to reduce testing requirements.
Okay. And Tamer Bashar has a question. He said your stability result was for the linearized model.
Yes.
are there conditions under which the linearized model captures for the full model?
That's a great question. We haven't looked at that, but definitely something to think about. Yep, very good question.
Okay.
And Juan Pablo still pushes back, saying, "But conservative, but it's actually better for detecting an infected agent." I agree. But I mean, if the budget of testing is an issue, then thinking about some more refinements makes sense.
Maybe. So it's a question from somebody you know very well, Ozan Chandawan. For those of you who don't know, Ozan was ASU student. Would it make sense to pool tests of the students in the same pod? If so, should we think about tests per pod or per student?
Yeah, so we were thinking about pooling. I mean, the testing I talked about, Ozan, was at the pod level. So we were basically testing one student per pod. Are you asking whether we should, and then we're removing it. So it's actually, so I don't know how to make a formal statement about that, but it's actually close to the pool testing, if that's what you're thinking about.
Yeah, I don't know. Ozan, do you have a further comment? You can type it in. Okay, maybe we can wait till the end, and if he has a follow-up, then we can take it then. Perfect. Okay, Francesca, please go ahead.
Okay, you can hear me now?
Yes.
I still cannot share my video, but maybe it's okay. I can just talk.
We would like you to share your video. Larry, can you enable share video for Francesca? I mean, she says she cannot share the video.
Okay, perfect.
Okay.
Perfect. Okay, so you see now, right?
Yes.
I assume. Okay, perfect. So in the second part of the talk, what I want to present is some partial results that we have derived with Azu and other people in the group about lockdown policies at the level now of a state over a country. So I'm like zooming out a bit from the model that Azu presented for university, and now we are looking at a state level. And one important thing that I want to mention is that lockdowns are significantly different type of intervention than what has traditionally been considered in epidemic and control literature. And this is because of this trade-off between the epidemic and the economic cost of the intervention. So this requires new modeling and new analysis. And there's been a number of recent work that started investigating in that direction. And in particular, these first two papers, for example, they look at the effect of lockdowns in simple SIR models as the one that Azu described in the first part of the talk. And then as part of this seminar series, you actually already heard about these two contributions, where they look at the effect of the lockdowns for more heterogeneous model, where you may have that agents are different because they have different risks, or maybe agents are different because they live in different locations. So what I'm gonna focus here is actually this model, this first one that was introduced by Alvarez, so for simple SIR models. And my objective here is actually to compare the performance of the optimal control with actually different type of policies that are based on indicators that are currently being used by governments. And really what we aim at in this project is try to give an insight of how should we use this indicator in order to design thresholds for reopening. Okay, so just to be on the same page, let me first review a couple of results that are well known about SIR models in homogeneous population. One slightly note here, I'm gonna express my dynamics in terms of normalized quantities. So these small s, small I, and small r here are gonna be the number of susceptible, infected, or recovered agents divided by the population size. So these are quantity between 0 and 1. And then exactly as Azu explained, you can write what is the dynamics of this quantity, and you can compute what is the reproduction number. Now, one important point that I want to make is the reproduction number, as Azu explained in the first slide, as the number of secondary infection was computed in the case when you take an infected person and you put it in a population where everybody is susceptible. Instead here, if we look at the dynamics over time, you have that the number of susceptible changes in time and actually decreases. So if you look at the number of secondary infection caused by an agent at time t, you actually have to scale this by the number of susceptible, because not all the interaction that these agents have are with susceptible agent, and so not all lead to secondary infection. And so the right way to scale it is by the percentage of agents that are susceptible, which is this additional term S of t. And why is this interesting at all? Because we can rewrite the dynamic for the number of infected in terms of this time varying reproduction number. And then you see that if this R0t is greater than 1, this term is positive, meaning the number of infected is increasing, while when R0 is less than 1, then you have that this term is negative and the number of infected is decreasing. And one important thing that I want you to note is the dependence on the susceptible. So remember, susceptible, it's always decreasing in time in an SIR model, which means the reproduction number is always decreasing in time. And so this means that if I start with a reproduction number that is greater than 1, I will have an initial phase when this term is positive, infected are going up, but at the same time, susceptible are going down. So at some point, I will hit the point where R0 is exactly equal to 1. And after that point, I know that R0 is less than 1, and so the number of infected will go down. So all of this to say that in the dynamics of an uncontrolled SIR model, you have this one peak where you have monotone increase of the infected at the beginning and then monotone decrease. And the point at which this peak happens is what is called herd immunity, which is a very important concept. So this is basically the time where the number of susceptible is such that R0 is exactly equal to 1. So after we reach herd immunity, we know that no matter what, the number of infected is going down. And as I mentioned, all of the things that I've just reviewed are for the uncontrolled case. What we want to study is what is the effect of lockdowns on this type of dynamics. And this is a model that was first suggested by Alvarez. And so what we can do is we can model as L of t, the fraction of people that are in lockdown, and by theta, the effectiveness of this lockdown. And by this, I mean that even if we put lockdown to 1, so we ask everybody to be in lockdown, we'll still have a little bit of mixing, either because of non-compliance or because of essential businesses. And so overall, we can say that the fraction of population that are free to mix is this 1 minus theta L. And so what this means is that I will have this fraction of susceptible people that are free to mix and this fraction of infected people that are free to mix, meaning that when I compute my force of infection, I have this term squared. And then I can compute what is the corresponding reproduction number for this control system. And exactly for the same reason, this is the uncontrolled reproduction number multiplied by this factor in red. And note that this is always less than 1, so that's why lockdown are helping. They are reducing the reproduction number. And so, for example, you see here, if I put a lockdown of 40% constant over time, what's happening is that I'm slowing down my dynamics, so I will reach herd immunity at a later time point, but I will also have a smaller peak. And so an important question now is, how do we design the optimal function of lockdown? And clearly, to define this problem, I first need to tell you how do we evaluate optimality. And we do this by computing basically what is the effect of the lockdown over a certain time horizon, 0t. And here I'm going to assume capital T to be the time for the vaccine, because we know that when the vaccine arrives, we actually don't need lockdown anymore because we can control the system with the vaccine. So we want to decide what's the optimal way to control my system until the vaccine. And now, in order to understand what is this cost, Alvarez suggested that we should consider 2 different contributions. So the first one is the economic cost associated to lockdown, because if I ask people not to go to work, I will have a loss because of loss of wages. And in this model, this is this parameter W, which we actually assume normalized to 1. And then, of course, there is an epidemic part, which is due to the fact that I actually want the lockdown in order to reduce the number of infected. And this second term here is basically proportional to the number of deaths that I have, which can be computed as the integral over time of the mortality rate times the number of infected. And note that here we assume the mortality rate to actually be state dependent, meaning that if I have more infection, I assume the mortality rate increases to capture the fact that the health system is congested. And then finally, you have this last parameter, kappa, which is the non-pecuniary cost of deaths. And this is, of course, very difficult to decide what this parameter should be. And we are not gonna actually ever study for one fixed parameter. The way we are gonna use this parameter is as a trade-off, basically as a weighting parameter to trade off economic and epidemic cost. Okay, some first observation when talking about actually generic intervention in epidemics is that this can be classified in two broad classes. So the first type of intervention is sometimes called suppression. Here the objective is to decrease the number of infected as fast as possible. So the idea here is that I want to contain the spread of my disease in a very short time horizon. On the other hand, a second class of policy is what is called mitigation. And here the objective instead is not to necessarily eradicate the disease as fast as possible, but slow the spread of the disease so that the health system, for example, can catch up and can handle the infected. And what I want to stress is that both these approaches actually have some pros and cons. Clearly, suppression is better in the sense of that it reduces the number of infection very fast, so it will reduce the epidemic cost. But it requires constant intervention. So if at some point while I'm doing this, I stop the lockdown, nothing prevents the system from having a second peak, either because I didn't really eradicate the disease, or maybe I have some infection coming from the outside. On the other hand, mitigation typically has lower economic cost and need less aggressive type of intervention. One of the, however, the disadvantage is that the disease is gonna take longer, so I will have higher number of infections. One thing that, however, happens with mitigation is that I build up my system towards herd immunity, and then I know that once I reach herd immunity, the system naturally will bring the infection down, so I'm robust now to infection coming from the outside. And one important thing that I want to stress, and this is actually from a very recent paper, a very recent article, is that different governments seems to have adopted policies belonging to different classes. So for example, if you think China or New Zealand, they adopted very strong lockdowns at the beginnings. They were able to contain the disease, and they had very long time without any new case. But however, we see that in some cases we can have second peaks. On the other hand, countries like Sweden, they had less stringent lockdowns, and this led to less of an economic price, and according to some experts, they seem to be approaching herd immunity. So really the point that I want to make is that not clear at this moment which approach is better. And so what we wanted to do is, first of all, try to understand the optimal control that I've described in the previous slide, to which of these class does it belongs to. And the first thing that, the first answer that you see is what I plotted here. So what we did here are some numerical simulations of the optimal control for different values of this parameter kappa that, if you remember, was weighting the trade-off between economic and epidemic cost. And one thing that I want to say is that these values that you see are for numerical simulation where we use these parameters here, but which we took from the literature. But there is a lot of uncertainty around these parameters. So whenever I show a plot of this type, I don't want you to focus too much on the absolute values that you see, but more on the trade-off. And in particular, for example, in this plot, one important trade-off is to understand what happens when I change this parameter kappa. So what you see in this plot is the overall cost expressed in terms of number of deaths. So this is related to epidemic cost, and economic loss. So this is related to the economic part of the cost. And you see this for different value of kappa, and you clearly see that the optimal control is significantly different for different ranges of kappa. So when kappa is large, we have low, very low value of deaths, but high economic loss. And if you look at what the optimal control is doing in this regime, is actually doing suppression. So it's keeping the lockdown constant active over all the time horizon in order to have very low number of deaths. However, as you decrease this parameter kappa, then you go into a second regime where instead you have higher deaths, but lower economic costs. And again, here, if you look at what the optimal control is doing, is selecting a mitigation strategy where it's trying to bring the system to herd immunity in an optimal way. And one important thing that I want you to note is that you have this type of transition if you look at the parameter kappa, but also if you look and change other parameters. So here, for example, I have the same plot where I change the length of the horizon, so the time to vaccine. And then you see that if the time until the vaccine comes is short, then it is the optimal control selects suppression. So since the time horizon is short, it's better to keep in lockdown until the vaccine comes. But after a certain time, if I need to wait too much for the vaccine, then it becomes beneficial to go for mitigation, so try to reach herd immunity in an optimal way. And one important thing that I want to mention is that, as you see here, it's greater than 1.5 because we tried several points, but the performance is always the same. And this is because of this fact that when I reach herd immunity, after that, I don't need to control anymore. So it really doesn't matter how long is my time horizon after that point. And so for simplicity, in our analysis, we are going to assume sometimes that t goes to infinity, but this plot suggests that the result that we obtain in that analysis should apply to the case where we have mitigation or we reach herd immunity. Okay, and a second observation that I want to make is that, as I mentioned, numerical simulations are very sensitive to the parameter that you're using, and therefore they provide no guarantees of what happens if the parameters are slightly different. Of course, an alternative to this is to use an analytic solution to the optimal control problem. However, this problem is actually very complicated, so an analytic solution is not tractable, and even if it was tractable, it may be difficult to translate into policies, into something simple that's connected to what's going on in my system. So because of this, instead, we consider simple policies that are based in either one of these two indicators. So the first indicator that we consider is the reproduction number, and clearly the idea here is that you want to contain the growth rate of your epidemic. While the second indicator that we consider is the number of infected. And this has been suggested, for example, not to overload the health system. And some advantages on focusing on these simple policies is that these indicators are currently being considered by governments to decide how to switch between different phases. And moreover, these policies that we are going to consider are closed-looped in the sense that the lockdown is strictly connected to the state of the system, and this should help in gaining some robustness to uncertain parameters. And so really our goal here is, first of all, to understand which policy, which indicator should we use to minimize the cost. And one important thing that I want to stress is that the contribution here is to understand this for the specific intervention that is a lockdown. In fact, there's been a lot of work in trying to understand these things for different type of intervention. Like, for example, for vaccine, there's a lot of contribution and try to understand how many people should you vaccinate, for example, to obtain stability of your system, which is really connected to the reproduction number. But these type of intervention are very different. For example, a vaccine has a fixed cost that you pay once, but then it has long-lasting effects. So the moment you vaccinate a person, this is going to be immune forever on afterwards, and you just have to pay at the beginning. Lockdowns are very different because you have to continuously pay. Like when your lockdown is effective only when it's active, and to keep it active, you have a continuous cost. And so this is a very different framework which requires new analysis. And of course, we also want to understand how these policies are related to the optimal control policy, and therefore understand how can we give insight on how to design phases for reopening. And so in order to answer this question, let me give you a little bit of details more about the policies that we are considering. So the first class of policy is based on trying to select the minimum possible value of lockdown to keep the control reproduction number below a desired threshold R0 max. And remember, the control reproduction number is just the reproduction number of your system times the value of the lockdown, or this factor. So if the uncontrolled reproduction number is already below the threshold, then you don't need any lockdown. You will select L equal to 0. While instead, when R0 is greater than 1, then clearly in order to select the minimum possible value of lockdown to satisfy this inequality, you have to make this as an equality, and this gives you a formula for the value of lockdown as a function of your threshold. And this is what happens if you choose, for example, a threshold that is below 1, then in this case, remember, you have that when R0 max is less than 1, the number of infected decreases. So this, you eradicate the disease very fast, but at the same time, you have to have a non-zero lockdown for all your time horizon. On the other hand, when R0 max is greater than 1, then what you allow is that you allow growth in the number of infected, But because of this, the number of susceptible is going down, which means that R0T is going down. There's going to be a time after which this is naturally below the threshold. So from that point on, you don't need to use the lockdown anymore. So the first question that we wanted to address is, what is the cost of such a policy as a function of this threshold? And so to analyze this, again, remember that we can divide our time horizon in these two phases. In the first phase, I need to control until my R0 arrives to be equal to the threshold. And after that the point, I don't need to control anymore. And clearly we indicate this with T star, and T star may be infinity if you never reach the second phase. So our first contribution is to suggest a method to compute the economic and epidemic cost for these two phases. So starting with the first phase, remember here we have an active control, and this value of lockdown is selected in such a way that R0 is actually equal to R0 max, which means that the dynamics actually become linear in this phase. And so this is a system that we can solve explicitly. The solution will be some exponential. So we can compute exactly both economic and epidemic costs using the explicit solution, as well as the state of the system at the time T star when we switch to phase 2. And then instead, if we look at phase 2, remember in this phase, we don't have lockdown, so clearly is zero economic cost. What is complicated in this phase is computing the epidemic cost related to these infections. And this is complex because the uncontrolled SIR dynamics is a nonlinear system, and there's no explicit formula for what is the number of infected as a function of time. So our contribution here was to propose a procedure to compute this epidemic cost, actually just as a function of the state at the two endpoints, so at T star and then at the endpoint. And just briefly, how do we do this? Remember, the epidemic cost is proportional to the number of deaths, which is the integral of the mortality rate times the infection. And remember that we assume the mortality rate to be affine, so we can actually rewrite this integral as an integral that depends on I and an integral that depends on I squared. And so what we're gonna do is try to compute these two integrals separately. So the first one is actually very easy. Note that, remember, I don't have an explicit formula for I, but from the third equation of my SIR dynamics, I know that I is proportional to the time derivative of R. And then if I substitute this back in, I see that this integral, I can compute it if I know the recovered at the two endpoints. On the other hand, to compute the second term, this is slightly more complicated. And what we use is a well-known fact that there is a constant of motion in your SIR dynamics, in the sense that this magenta quantity is constant in time. And the way you see this is just by computing the derivative and seeing that it's equal to 0. And so what this means is that if I know this constant, which I know, for example, if I know the initial state of my system, I can compute either I or S as a function of the other variable. So in this case, for example, I can express I as a function of S and this constant K. And then using this relation, I can substitute this value of I in one of the two terms of this I squared to obtain this expression here. And note that here it seems I made things worse because I started with one integral and now I have 3. But actually the last one we already studied, we know how to solve this. And for these two, note that again here we have an I term that is as an argument. But looking at the first equation of the SIR dynamics, I can now express this I as a function of S and it's the time derivative. And so if I plug this back in my integrals, I will have that these are of the form of function of S times the time derivative of S. So if I can compute a primitive with capital F of this function small f, again, I can compute this integral just by knowing the state at the two extremes. And so now overall, I know how to compute this if I know the state at my extreme. And coming back to the phase 2 dynamics, as I mentioned, we know the state at T star because we can compute it explicitly. And if we let the time horizon go to infinity, we also know that the number of infected at the end will be 0. And from the constant of motion, we can compute the number of susceptible at the end point, meaning we have all we need to compute the epidemic cost. So overall, basically for every value of the threshold R0 max, we are now able to compute analytically what is the associated cost. And of course, the best policies to use is the one for threshold that minimize the total cost. So I'm gonna denote by star the policy belonging to this class that minimize the total cost. And so this will be my first candidate policy. As I mentioned, we're also considering a second class of policies, which is based on the number of infected. And here the idea is again very similar. So what we're gonna assume is that we want to select the lockdown in order to keep the number of infected people below a desired threshold Imax. And this is a problem actually that's been studied before in the literature, and the optimal solution to this problem is to actually not control at all my system when I is below the threshold. And the first time that the number of infected reaches the threshold, then I'm gonna start selecting the lockdown such that the number of infected remains constant at the threshold. But remember, since the number of infected remains constant, it means the number of susceptible is going down. So there's gonna be a point in time where I reach herd immunity. And from that point on, I know that naturally the number of infected goes down. So when I reach herd immunity, I is gonna go down if I select a control that's 0. And one important thing that I want to stress, in this paper, they solved this problem for a fixed threshold of Imax, which in their case was given by the ICU constraint. What we want to do is we actually want to optimize over this threshold. We want to select the value of Imax that minimize the total cost introduced by Alvarez. So again, we need to find an analytic formula that connects the total cost to the threshold that you are choosing. And again, we can do this by dividing our time horizon into phases. So remember, in the first phase, we have uncontrolled dynamics until I reaches Imax. So we can solve this exactly as I explained in the previous slide. In the second phase, we have that Imax is constant. So computing the epidemic cost is very easy. And at the same time, we also had that the control dynamics turn out to be a linear system. So we can compute explicitly the solution and the economic cost. And then leads us to the third phase, which again is uncontrolled, and I can compute economic and epidemic cost as I've described before. So overall, we know how to have an analytic expression for every threshold Imax, and we can define again Imax star as the one minimizing this cost. And so overall now what we have two candidate policies for which we can compute the associated costs. And what we did was also to derive, since we want to compare this with the optimal control, we derive an analytic lower bound for the performance of the optimal control. And so what you see in this slide now is the result of this, so the total cost that you get under this policy as a function of this weighting parameter kappa, where blue is the one where I control R0 to the best possible threshold. Magenta is the one where I control the number of infected to the best possible threshold. The dots here are the total cost associated with the optimal control evaluated numerically, and then the yellow is our lower bound. And here there are two things that you may observe. So first of all, at least for this parameter, it seems that the controlling the number of infected leads to better performance than controlling R0. And also this seems to be very, very close to the optimal possible control. And in this plot here, I'm just plotting the total cost, so the value of the integral, but you can actually look at what the lockdown looks in time. And so this is what I plot here, focus for the moment in the right column. Is for some values of the parameter, you see, again, in magenta is the lockdown controlling the number of infected, and in orange is the optimal. And you see that these are actually leading to very similar lockdown also as a function of time. While instead controlling the reproduction number has a different shape, which also leads to very different transient for the number of infected. And then on this left, on the other end, I plotted different values of parameters for which instead of mitigation, the optimal control does suppression. And the conclusion seems to be similar in the sense that controlling number of infected is still better than controlling R0, but all these policies are very, very similar in this case. So I wouldn't say this is a significant difference. So to conclude, basically what we did is to derive analytical expression for total cost of policies based on controlling number of infected or controlling the reproduction number. And it seems that controlling the number of infected outperforms controlling the reproduction number for lockdowns, at least in the case of mitigations. And the nice insight is that governments are already considering policies where they switch across different phases based on the number of infected. So this analysis may suggest how to select this threshold to account not only for the epidemics or the congestion of the health system, but also to incorporate into this threshold the economic trade-offs. And as I mentioned, this is some preliminary work. So right now we are working to provide guarantees of near optimality for this policy based on the number of infected. And moreover, we plan to extend these analyses and build on these studies to look at a heterogeneous network model where you may have population with different level of risk or different locations. Okay, so this was it. And thank you so much. If you have any question, I'm happy to reply.
Thank you very much. It's a great talk by both. Thank you both, Asu and Francesca. So there are a couple of questions. Maybe we'll just take these three and then wrap it up in the interest of time. So I guess you did mention herd immunity, and Juan Pablo Gutierrez asks, is it possible to incorporate a parameter for reinfections that may imply that herd immunity is not feasible? But I guess reinfections are still not, it's somewhat controversial, but yeah. Maybe
yes, it's controversial. I guess in that case, I actually read a recent paper by Naomi Leonard where they had this model SIR and then S again, so that you are recovered for a place and then you can get infected again, or you would go directly for a simple SIS model, I guess. So it's changing a little bit the dynamics, but that's possible. We will have to see how the results change, though, of course. We analyze the SIR dynamics for now.
Okay. And I guess the next question is maybe for the first part of the talk. So sorry if I missed this earlier, but in the pod analysis, did you look at heterogeneity in pods compliance rates? If so, how does increased heterogeneity change the required time between tests for each pod?
Yes, okay, can I start everything? Okay, so yes, indeed, we can incorporate heterogeneity. That's exactly the model. The numerical results I showed you were for one pod and the two pod case. In the two pod case for FSILGs versus dorms, they are different. We can capture different compliance rates, and they will tell you different testing rates for dorms versus FSILGs. If people are partying a lot in one place, we can definitely test them more. And the model exactly incorporates that heterogeneity.
Okay, thank you. So I think the next question is again by Juan Pablo Gutierrez. And this is, I guess, maybe relevant to the Francesca's part. I'm assuming that you're considering the horizon both with respect to vaccine as well as to the effective therapy that reduces mortality. I guess
yes, I mean, in some sense, this is the time horizon where you can expect some pharmaceutical type of intervention. So when we don't need to rely anymore on just lockdown and social distancing.
Okay, great. So the final question is by Rosena Baichi. So did you compare your model with some real data? How do they agree with ATW? I don't know what that is. How do they agree with real data? Yeah.
I mean, we did not. We took parameters from people that did that. So like the parameters that we use in some sense were from there, but no, we didn't really compare. And in some sense, it's also, that's a little bit different because it's what we are suggesting is something that didn't happen, right? It's not just a model of what happened in the past. We're saying you should do this type of lockdown. So it's dependent on what government do.
No, but the parameters we use are from data, right? So the model is calibrated using real data, but the implications, of course, is, we're considering different policies, and would be great to see, if people can actually use these policies, and then, we can then have the data to compare our results with.
So is MIT using pods actually, or are they?
They are not to the level of this, but they went with a more conservative structure. But a lot of this analysis did inform the policies they made. So that's why we were excited to talk continuously with the chancellor and the heads of houses and things like that. And awesome. So it's not, they're using very small pods, but not extensively across the dorms, but they're using some pods.
Okay. So I guess there is one comment. It says, my apologies. I guess Juan Pablo Gutierrez is apologizing for asking too many questions, perhaps. He's saying actually the questions half of them were from Steph Bertacci and they just logged in together. So, and then Saurabh Amin says, thank you very much, Asu and Francesca, for wonderful talks and great answers to questions. Congratulations.
Oh, thank you, Tara. Wonderful, thank you.
So we'll end it on that note. Thank you so much. That was a wonderful talk. And next week, the talk will be by Zoe Rapti, and I hope to see many of you there. Thank you. Bye.
Thanks for having us. Bye-bye.